Hello, so today we're going to start learning about trig identities. So to start, I just want to review what the word identity means in math. So in math, an identity is a statement of equality between two expressions, which is true for all values of the variable. So start with two that we're pretty familiar with. 0 times x is 0. Really, 0 times anything is going to be equal to 0. And the second one, if I have x cubed, that means x times x times x. So hopefully those are two we're familiar with. We're going to throw the word identities out there a lot in this unit, which is why I wanted us to be comfortable with the definition of identity. So the first things we're going to talk about is ones that are pretty familiar with to us: sine, cosine, and tangent. So I'll even write SOHCAHTOA up here. I'm going to use some colors to remind us of the three that we already know. Right? That sine is opposite over hypotenuse, cosine can be represented as the ratio adjacent over hypotenuse, and tangent as opposite over adjacent. So reciprocal, well, let's review what the word reciprocal means. So over here I'm going to do an example of two things that are reciprocals of each other. So for instance, if I have 2/3 as a fraction, its reciprocal means I'm going to flip the numerator and denominator. So the reciprocal of 2/3 would be 3/2. Now the nice thing about reciprocals is when we multiply them, they result in 1, right? 2 and 2 reduce away, and so does the 3 on top, the 3 on the bottom. You could also make it 6 over 6, which reduces to 1. So when we talk about these reciprocal identities, let's start with sine. Sine, I'll use theta, but we could use x, can be represented as 1 over another trig function. And that trig function is abbreviated CSC. And that CSC stands for cosecant. And it's the reciprocal of sine. Another way to write this would be if we wanted the cosecant to be our numerator, then we could say that's equal or equivalent to 1 over sine. And a third way to represent them is if we multiply the two, just like our example 2/3 times 3/2, well, two reciprocals being multiplied equal 1. So that's the sine example. Let's go to the cosine reciprocal identity now. So the reciprocal of cosine is something we call secant. Now that one should be a little bit more familiar to us because we've learned about it when we learned about secant lines in past math topics. So I can write cosine of theta equals 1 over secant theta, or secant theta equals 1 over cosine of theta. And just like the sine times cosecant was 1, cosine of theta times secant of theta is also equal to 1. Our last one is tangent. So tan of theta has a reciprocal called cotangent. And it's abbreviated COT. So COT stands for cotangent. So I can also say that cotan of theta equals 1 over tan. And just like the others, if I multiply two things that are reciprocals of each other, they equal 1. So those are my reciprocal identities. In a minute, we'll practice simplifying with those. But first, let's go to our quotient identity. So the word quotient hopefully looks familiar to us, right? A lot of you think of division when we think of quotient. So that is true. We're going to actually be focused on division here. So the quotient identities that we're going to talk about are tan of theta and cotan of theta. Now, before I actually tell you what their identities are, let's think about what the relationship for tan is. Because in the past, we've learned a lot about tan. And one of the things we learned was when we talked about triangles or points on a circle, we often thought of tan as y over x. Well, that's true. But remember, y we also thought of as our radius times sine of our angle. And x was our radius times cosine of our angle. So if I replace y with radius times sine of our angle, and x with radius times cosine of our angle, that is also a true ratio. In the radius, since they're the same, I can actually just reduce those away. So tangent actually simplifies to sine of theta over cosine of theta. Well, cotangent, remember, is the reciprocal of tangent. So if tangent of theta can be expressed as sine of theta over cosine of theta, that means cotan of theta can be expressed as its reciprocal, cosine of theta over sine of theta. So those are our quotient identities. Okay, now the next one we're going to do is use the unit circle to identify Pythagorean identities. So we're going to come up with 3 of these. So I'm going to kind of put some stars over on the side so we can list these. I'm going to double star the first one, and we'll see why in a minute. And now I'm going to go ahead and draw a unit circle. And I actually might not do a unit circle. I might just do a regular circle. It doesn't have to be the unit circle. So my drawing is not to scale here, but that's okay. We can imagine this is centered at 0, 0 there. So I'm going to draw a terminal ray coming out, and I'll just use the first quadrant, but it can be any quadrant. I'm going to make a triangle here. So just like before, this, whatever the radius is, this y length is our radius times sine of theta, and hopefully that's familiar to us from past lessons. And this x value here, remember this is the xy point, is our radius times cosine of theta. So in a right triangle, you've probably heard a squared plus b squared equals c squared, right? The Pythagorean theorem. Well, in our scenario, I have one of my sides is x squared, the other one is y squared, and I have my radius squared. But I can replace x with r cosine of theta, and I can place y, it might be off the screen here, sorry, y with r sine of theta, sorry. And I'm going to leave r squared as it is. Well, if I distribute that square, I get r squared times cosine squared plus r squared times sine squared equals r squared. Now, the neat thing about these is we know, since this r is a hypotenuse, it's a length, we don't know what r is, but we know it's some positive quantity. And more importantly, it's not 0, otherwise we wouldn't have a circle there. And we wouldn't be able to form a triangle. So I'm going to divide everything by r squared, which I'm allowed to do since we know that r is not 0. That leaves just cosine squared plus sine squared, and r squared over r squared is 1. So that is one of our 3 Pythagorean identities. So I'm going to rewrite that. And just to show it doesn't matter the order, when I write it here, I'm going to write it with my sine squared first. It truly doesn't matter which one comes first. And we're going to spend a lot of time this term sort of manipulating all of these identities. Equals 1. Okay. So that's the first of the 3 trig identities, Pythagorean identities that we want to learn. Now, to get the others, we're actually going to use what we already have. So I'm going to come over here for a minute, and I'm going to take that same cosine squared theta plus sine squared theta equals 1. But this time, I'm going to divide everything by, let's do cosine first. There's not a right or wrong one to go first. I'm going to say, I'm going to divide every single term by cosine squared. Well, 1 over cosine squared over cosine squared is 1. Sine over cosine, we just learned that that's the same as tangent. Since they're both squared, it stays tangent squared. And we just learned that the reciprocal of cosine is secant. So from that cosine squared plus sine squared equals 1, I was able to find another form of the same identity. 1 plus tan squared equals secant squared. So I'm going to go over here and write it underneath there. 1 plus tan squared theta equals secant squared. And you'll see these written different ways sometimes. Sometimes you'll see secant squared minus 1 equals tan squared. You can manipulate them. You can move the 1 to either side as long as both expressions are equivalent. Okay. Now, I decided to multiply first by divide through by cosine. But let's see what happens if I divide everything by sine instead. And I just decided to write sine squared first plus cosine squared. You could have, again, written the cosine first. But on that previous example, I divided everything by cosine squared. So on this one, let's divide everything by sine squared. So now we see sine over sine is 1. Cosine squared over sine squared, well, that is cotangent. That's another quotient identity. And the reciprocal of sine is cosecant. Cosecant squared. So there's another Pythagorean identity. Again, it comes from that concept of sine squared plus cosine squared equals 1. So I'm going to write it in our line with the others. So this one was 1 plus cotangent squared was equal to cosecant squared. Okay, so those are the identities we're going to start with. We're going to learn more later on. There's so many different trig identities, but these are at our beginning the most important ones to know so that we can really get comfortable working with all 6 trig functions. So we're going to practice simplifying these with these 2 examples right here. And I'm going to do each one using 2 methods. There's a lot more than 2 methods that we could use. And you certainly don't need to do them 2 methods, but it's good to see multiple options. So I'm going to say this is method 1 and method 2. One of these is not more important than the other or better than the other. It just sort of goes to what your brain sees first. So first I'm going to rewrite this. Tan of x, cos of x. I actually don't need the parentheses there, but it doesn't hurt to include them if you want to keep them. So there's that original problem. And basically, when we start these, we want to look for any identity we might be able to point out. So maybe you see cosine over sine first, because remember in algebra, as long as there's no addition and subtraction, I could separate that tan out. I could make it its own fraction and keep the sine x on the bottom here. These come out to be exactly the same if I separate it like that. So tan, I'm going to keep that as it is. But I might notice that cosine over sine, well, that was one of the quotient identities, right? Cosine over sine is the same thing. It's equivalent to cotangent. So I'm going to replace cosine over sine with cotangent. Okay, anytime we do a replacement, it's good to sort of look at what we have now and see if we can see any more identities. So for this one, we use that quotient identity. But here, I might notice that these are reciprocals. So when I see that they're reciprocals, when I multiply 2 things that are reciprocals, remember from before we said that those equal 1. And that is as simplified as I could possibly make this expression, breaking it down to be just the value 1. So now let's look at this from a different angle. So tan x, I'm actually going to still start with breaking it up into 2 pieces. We certainly don't have to. Actually, I'll break this up into 3 pieces to show that you can. If you wanted to write this as 3 separate pieces, you can absolutely do that. And one common method for solving these that some people use is to turn everything into sine or cosine. Now, this isn't always going to be the most efficient method, and sometimes this doesn't work out super well, but it is a method that works a lot of the time. So if we're using this method, well, these are already sine and cosine, but I can change tangent to be sine x over cosine x. Now, I still have this cosine x, which I don't have to write over 1, but I think it really helps to remind us that it was in the numerator, and sine x was in the denominator. So now that I have everything in terms of sine and cosine, I want to look for any terms that reduce. So sine on top, sine on bottom, those go away. And cosine on top, cosine on bottom, those goes away. I'm left with nothing other than 1s. 1 over 1 is just 1. So whichever method sort of spoke to you better is totally fine. There isn't one that's better than the other. It's just recognizing that we could use that quotient identity in a different way. So that was the same quotient identity. Just used to go from tan into sine over cosine rather than cosine over sine to cotangent. Okay, I'm going to go to our next example. And once again, I'm going to do this one using 2 strategies. So just separate our notes there. So method 1 and method 2. So for method 1, we're going to look for an identity right away. We're going to see, is there already an identity that I can replace before I do any algebraic work? So that kind of brings us in, actually there's 2 places we could see them, but I'm going to look at this one here because I'm going to remember that I had an identity that said sine squared theta plus cosine squared theta equals 1. And that's clearly not what I have right here. I don't have either a sine squared plus cosine, and I don't have just a 1. But I can manipulate this to be what I need it to be, right? I can take this cosine and move it to the other side. That would give me sine squared alone on this left side, and 1 minus cosine squared on the other. If it's positive on one side, when I move it to the other, it's going to be negative. So that allows me to replace this. So I didn't touch my secant squared yet, but that whole set of parentheses can become sine squared. I just had to manipulate one of my Pythagorean identities a little bit. Okay, from here there's a few ways we can go as well, but falling back to that thing I said on our last example of if you're kind of stuck, turn things to sines and cosines is a good rule. This can be 1 over cosine squared. Well, now I have a sine in the numerator and a cosine in our denominator. So I'm going to combine those to one fraction and realize that, hey, there's a quotient identity. I can make that tan squared theta. And once we get it down to a single trig identity, it's a pretty good indication that we can't go much further. So we're going to stop there. So that's one method for solving this. And for this one, it's really difficult to do it without using a Pythagorean identity, but I'm going to show you one way that maybe uses the Pythagorean identity a little bit differently. So maybe you're looking at that trig function and you notice, hey, there's multiplication here, right? Parentheses with something outside of them tells me to multiply. So maybe you want to start by multiplying secant of theta in. Well, that's perfectly fine. 1 times secant of squared theta is just secant squared theta minus secant times cosine. I'm going to write that out. Secant times cosine squared. I can't actually combine those together any more than that yet. Okay, so there is a relationship between secant and cosine, right? These are reciprocals. Remember we said when we multiply two reciprocals together, they equal 1. So that allows me to make this secant squared theta minus 1. So we have another Pythagorean identity that tells us that 1 plus tan squared theta is equal to secant squared theta. And once again, it's not exactly what we have on our page, but if I want this to be secant squared minus 1, I can move that 1 over to the other side. Then that leaves only tan squared on my left side. And my right side becomes secant squared minus 1. So that means that this whole thing can be replaced with tan squared theta. Okay. So hopefully those two examples give you an idea of how identities can be used to simplify trigonometric expressions. Thank you for watching.